This presentation I'm going to be talking about is based on work that my co-author, Professor Mike Schleier, started more than 25 years ago, looking at the long-term changes in coral communities up at Sodwana Bay. So what I'm going to do is give you an overview of the type of coral reefs we have in South Africa. We're then going to look at the methods we've used to monitor these reefs. I'm going to highlight the most important results and interesting trends, and then I'm going to try and provide some reasons why we are finding these trends on our reefs. Okay, so South Africa has a relatively small amount of coral reef of approximately 40 square kilometers in extent, and these reefs are located in the extreme northeastern parts of the country in the Delagoa Bay region. They are scattered among three main reef complexes along a coastline of 120 kilometers. Importantly, they all lie within marine protected areas and a World Heritage Site, the Isimangalisa Wetland Park. They are also the southernmost coral reef communities on the East African continent. As such, they are marginal, they're high-latitude reefs, and they're non-accretive. They exist on fossilized sand dunes with a thin cover of coral at depths of between 8 and 27 meters. Despite being marginal reefs, they are nevertheless high in biodiversity, with at least 90 species of hard coral and 40 species of soft coral having been recorded. The map on the right just shows you the distribution of the reefs in yellow, and the study site or the monitoring site is located in the central reef complex around Sodwana Bay. And then the image on the bottom left just shows you a typical coral reef community that we're monitoring, and they are largely dominated by soft corals. So the high biodiversity value and ecotourism potential of the reefs in the Sodwana region were recognized early on, and as such a long-term monitoring study was initiated. And it was during a time when there was growing appreciation for global change, particularly anthropogenic climate change. So the aim of this monitoring study was really to look at the condition of the reefs over time, and also try to relate it to any climate change impacts. So 4 permanent transects marked with beacon pins were laid on 9 Mile Reef. The transects range in size from 1 to 6 square meters and total 15 square meters. For any given year, the average number of coral colonies that were monitored were 350, and the transects were also accompanied by an underwater temperature recorder at 18 meters depth, which has been continuously monitoring temperatures since 1994. The map on the left just shows you the transects in black from B to E, and on an annual basis the transects were photographed using 0.5 meter by 0.5 meter square quadrats. The other images just show you the underwater temperature recorder in the middle when it was first deployed, and then the bottom there what it looks like now, and then these are just examples of the beacon pins, so we can actually monitor exactly the same part of the reef and pick up very small changes. Okay, so I mentioned the transects were photographed annually, and then the quadrats themselves were actually stitched together digitally using analysis software, and this is what we get when we merge all the images together. So these are 2 examples of transect E and transect C, and immediately you can see the different corals within them. What we do then is we input these transect images into a GIS software, and we georeference them to the original baseline transect, and then we meticulously digitize each coral colony and give it a unique ID number, and we can actually track what it's doing through time. We can also detect when there are any new coral colonies, so we can look at recruitment, and if any coral colonies die, we can also look at mortality. And the actual size of the coral colonies are then converted to a percentage cover. So this is just an example of a turbinaria coral, and what it looks like when it was first measured in 1993, and how it's grown through time, and how the graph reflects this. So we can very accurately quantify growth of all these corals and look at any patterns over time. Okay, so moving on to the actual analysis. The temperature loggers were storing hourly means, and from that we could compute monthly averages, monthly max, and monthly minima. And then in order to actually visualize the temperature data, we used classical time series decomposition, so we could isolate the trend, the seasonal, and the remainder components. We then were interested in whether there were any trends in the average temperature, the maximum temperature, and the minimum temperature. And for that, we used ANOVA models to test for differences in the sums of squares or the residuals of two mixed effects models. A full model, which consists of year, time, and a trend component, and a reduced model without the trend. The trend component is simply an explanatory variable that tracks each datum in the time series in a linear fashion and was treated as a fixed effect along with time. Year was included as a random categorical effect, allowing for different intercepts for the different years. We were also obviously interested in how the community actually changed through time. So in order to visualize this, we used non-metric multidimensional scaling based on Bray-Curtis similarities to project each year in multidimensional space. We then tested whether there were differences between the communities quantified in the first 3 years of monitoring versus the communities quantified in the most recent 3 years using a one-way permutational multivariate analysis of variance. This test was then supplemented with a permutational multivariate analysis of dispersion to test if there were location or dispersion effects. We were obviously also interested in testing whether there were trends in the soft or hard coral percentage cover, recruitment success, and mortality. So we performed linear regression analyses with serial correlates and did a test of the fitted line. And this involves fitting autoregressive moving average models with a drift term. The goodness of fit of each of these models was then evaluated by plotting the autocorrelation and partial autocorrelation functions and doing Lundbach's Portmanteau tests, and the results was just to make sure that there was no remaining autocorrelation. Because the observations through time are not independent, and this is a mistake a lot of people make. So they get false positives. Then we were also interested in whether temperature was actually driving any of these patterns. So we used simple Pearson correlation coefficients between the yearly average and the yearly maximum temperatures versus soft and hard coral cover. All these analyses were done in R and Permanova plus for primer. Okay, so these are the results of the temperature analysis based on the monthly averages. And the top panel shows the observed data, the monthly averages, and we can see that there's definite periodicity in the data. The values range from 22 to about 28 degrees, but I think you'll agree with me, there's no obvious trend there. It's very difficult to see what's going on. There's so much other temporal and seasonal variation. So then with the classical decomposition, we can actually isolate just the trend component. It's simply just using moving averages. And if we look at the trend component here, we see that temperatures are generally warmer in the beginning of the time series. This hump corresponds with the 1998 bleaching event when there was a very strong El Nino event. And then subsequent to that, temperatures have generally decreased, but it has meandered somewhat. The panel below that shows you the seasonal component, and very obvious seasonal component as you might expect from a high-latitude reef. And then the remaining component is on the bottom there, and there's some low spikes there that actually correspond with periodic upwelling events that you get in our reef. Then what I've done here for the top table, I've just taken the first half of the temperature data and compared it to the latter half of the temperature data for these three parameters: monthly average, monthly maximum, and monthly minima. And what I want you to see here is that in all three parameters, the first half of the time series is warmer than the latter half of the time series. So immediately this is actually telling you that things have been cooling at the site over the last 20 years. We can then test whether these trends, these cooling trends, are actually significant. And that's the result at the bottom here. And we find that for both the monthly average and the monthly maximum, the trends are decreasing and significant, whereas the monthly minima, although it is also negative and decreasing, it's not quite significant. Then if we look at the multivariate community analysis, this is the MDS plot, and we can see quite clearly how the community, when it was first quantified in 1993, has actually been quite dynamic and is shifting in multivariate space through time, and is not constant. It's fluctuating, it's dynamic, and it's actually been through times becoming more and more dissimilar from the baseline community originally measured in 1993. And this is Sorry. Are people battling to hear me? Okay, so this analysis was supplemented with a similarity analysis where we compared the similarity between the baseline year and successive years, and we found that there was also a significant decreasing trend here. And then Permanova detected a significant difference between the original 3 years and the most recent years monitored. Okay, this graph just shows you the trends in soft and hard coral cover. The top line shows you the trend of decreasing soft coral cover, which was found to be significant, and it equates to about 1% per annum, so a very, very subtle change in soft coral cover that in reality equates to 150 square centimeters only. Contrastingly, the hard corals, which is the bottom line you see, there was a very gradual yet significant increase in hard coral cover, but after about 2005 it's since stabilized. Okay, so these are just percentage cover graphs of the most abundant and representative genera, and we see that the Sinularia and Lobophytum are the two main soft corals that are actually decreasing and contributing to the general decrease in soft coral cover. With regards to the remaining genera, these are hard corals, and most of them are increasing, but it's only really the Acroporas that are increasing significantly, but very, very gradually. This graph shows you recruitment success and mortality. The very top graph shows you those results for both soft and hard corals together, and you can see that there's a lot of variation in time. Both trends are positive, but neither are significant. If we just look at the hard corals by themselves, we see this massive spike in recruitment in 2010, followed by a slow increase in mortality. Again, both trends are positive, but neither are significant, I think, because of the high amounts of variation. And then if we look at soft corals, we actually have two spikes in recruitment around 2006 and again around 2010, 2012 that are mirrored by increases in mortality almost a year later. So perhaps because there's more juvenile corals, there's actually there's more chance of them dying. So that's what would increase the mortality there. And both these trends are, again, they're positive, but because of all the variation, they are not significant. Okay, so these are just correlations between the average yearly temperature and soft and hard coral cover. And we see that for soft corals there's an increasing relationship with temperature, but not quite significant. Contrastingly, for hard corals there's a decrease in cover with increasing temperature, but again not quite significant. And then if we look at this relationship with maximum temperature, which is often more important because it's the maximum temperatures that actually drive the major changes, we find that there's even poorer relationships for both soft and hard corals. Okay, so just to summarize here what we've actually found, we found a decreasing trend in temperature based on the monthly averages and the monthly maxima that equates to about 0.3 degrees per decade. Okay, so it's very, very small, nevertheless significant. The community is certainly dynamic, and it's actually decreasing in similarity from the initial survey year. This is largely being driven by a consistent decline in the cover of soft coral at about 1% per annum. Contrastingly, we've got an increasing trend in hard coral, which has since stabilized since about 2005. So what factors could be driving these patterns and trends? With regards to temperature, we just need to bear in mind that 22 years or so is actually a relatively short time to be monitoring temperature. This is probably just a shift between periods and the timing of El Niño events. So if you recall that there was a large spike in the beginning of the temperature series which corresponded to a very strong El Niño, and because it was in the beginning of the temperature series, subsequent temperatures have been cooler, and that's just shifted the graph and caused a decreasing in trend. So this might be a short-term period of decreasing temperature in a much longer general period of increase. So that's important to realize and understand. We obviously need more data, more time to obviously know what's going on. With regards to the changes in the community structure, it's difficult to say at this stage what's causing the decrease in soft coral, because it doesn't seem likely that it's temperature, because I showed you there was no correlations there. It's not bleaching, because we actually haven't found any bleaching in the transects at the monitoring site to actually cause mortality. Another possibility could be long-term exposure to pollutants, but this also seems very unlikely because there are no major industries in the area, there's no rivers to act as conduits for pollutants, and then these reefs are also very turbulent, so any pollutants, if they are there, they get diluted very quickly. Long-term exposure to ocean acidification is a possibility. Soft corals, they are comprised of sclerites, which are made up of calcite, which is actually more soluble than aragonite, which is what the hard corals are comprised of. And because these soft corals are at their limits of their thermal range, they may have less energy for actually regulating the internal pHs to create an environment conducive for calcification. We are trying to get some funding to do those types of experiments at ORI. Another possibility could be competition between soft and hard coral covers, but this also actually seems unlikely based on the evidence we have, because the soft corals are not being replaced by hard corals or macroalgae. So we have these interesting trends and significant results, but at this stage we haven't been able to link them to anything tangible. So it's got us thinking a lot. Lastly, I'd just like to thank these following organizations for funding and their support. Thank you very much.